So we have now taken a look at derivatives, and we've defined them using a limit definition of a derivative, and we've done some calculations of finding the derivative of a function. And what we started to notice is the algebra involved in calculating these derivatives using the limits can get pretty complicated pretty quickly. So what we want to be able to do is see if we can come up with some rules that are going to shorten up that process of finding a derivative for us. So that's what this is going to be about, finding some basic differentiation rules. So the first one we're going to talk about is the constant rule. And the constant rule says that d dx of c equals 0. And if you remember, we discussed the fact that we are going to start to kind of mix up some of this notation. So remember what this says. d dx means you're about to take the derivative of c, and that's the derivative with respect to x. So when you take the derivative with respect to x of c, you get 0. Well, because this derivative is with respect to x, that means c represents a constant. So this says the derivative of any constant is going to be 0. That's the constant rule. This is all assuming that c is a real number. If c is imaginary, we have to rethink it a little bit. But for now, we're just going to deal with real numbers. So the derivative of any constant that's real is 0. So there's a geometric argument or a graphical argument to support this. If you take a look at the graph of any constant function, what does the graph of a constant function look like? Well, it should be a horizontal line. The horizontal line, y equals c. Whatever that constant is, y will be equal to it. So when you talk about the derivative of this constant function, if you're looking at its graph, you're talking about the slope of its tangent lines. Well, if you start looking at the tangent lines, it doesn't matter which x value you're looking at. The tangent line to a constant function is always going to be horizontal. And what's the slope of every horizontal number? Well, it's 0. So that's why the derivative of any constant is going to be 0. So that's the geometric argument. There's a much more rigorous argument for it. So here's the mathematical proof of it. If you let f of x equal c, and again, you can tell c is a constant because we have said f of x. That indicates that x is my variable. So there is no x on this side. It's a constant function. Then the derivative of f at x, which is, here's your limit definition that we've been discussing. It's the limit as h approaches 0 of f of x plus h minus f of x all over h. When you go to calculate this derivative, what is f of x plus h for a constant function? Well, the constant function is constant, so it's c. That's where the c comes from. What is f of x for the constant function? Also c. So in other words, your numerator becomes c minus c, also known as 0. So what you're taking is the limit as h approaches 0 of 0 divided by h. Well, that's the limit of a constant, which is the constant. So that's the mathematical proof. When we use the constant rule, we find things like the derivative of 5 is 0. No surprise. The derivative with respect to x of e is 0. Here I intend e to be the e that you're used to when you're looking at natural bases of exponentials or logarithms, that 2-point something number. But even though it's written as e, e represents a specific number. So its derivative with respect to x is going to be 0. The derivative with respect to x of a. Notice I didn't tell you what a is, but as soon as you see that this derivative is with respect to x, a is a constant, so its derivative will be 0. So that's the constant rule. The power rule is the next one we're going to make lots of use of. The power rule says the following. If f of x equals x to the n, so let's look at that for a second. F of x, that means my variable is x, which makes n a constant. So this is x raised to some power, and according to the last few words in this, this rule applies for all real n. So that exponent has to be real. then the derivative of f with respect to x is going to be n times x raised to the n minus 1. In other words, the exponent drops down in front and is written as a coefficient, and then x is raised to a new power, and that new power is exactly one less than the power it started with. Let's take a look at an example. So if you have f of x equals x cubed, then the derivative of f of x is 3, take the exponent and drop it down as a coefficient, times x raised to the new power, which is 1 less than 3, also known as 2. So the derivative of x cubed is 3x squared. For f of x equals x, remember that is technically x to the first power. So if I put in an intermediate step, I would drop 1 as a coefficient. I would have x to the new power of 1 minus 1, also known as 0. But what is x raised to the 0 power? Well, that's just 1. So this becomes 1 times 1, also known as 1. So the derivative of x is 1. If you have f of x equals 1 over x squared, now we don't technically at this point know how to take the derivative of a function that contains a ratio. But what you can do is you can rewrite this as f of x equals x to the negative 2. That's using the exponential rule that says if you have a raised to the negative m, that's the same thing as 1 over a raised to the positive m. I've actually just used it in the reverse order. So instead of writing this as 1 over x squared, we can write it as x raised to the negative 2 power, and then apply the power rule. Drop the negative 2 in front as a coefficient, times x raised to the negative 2 minus 1, which is negative 3. So the derivative of 1 over x squared is negative 2 over x cubed, or negative 2 times x to the negative 3. For f of x equals the square root of x, again, we don't really know how to take a derivative of a function that involves a radical. So what we want to do is rewrite that radical in a way that's going to allow us to apply the power rule. What you have to keep in mind is this little rule right here. In general, when you have something raised to the m divided by n, so that's a fraction in your exponent, that is the same thing as the nth root of a raised to the m. It's also the same thing as the nth root of a with the m on the outside of the parentheses. These are interchangeable. Traditionally, we're probably going to use this one a little bit more. It saves us some simplification along the way. But this is the relationship between fractions and exponents and radicals. So when you see f of x equals the square root of x, keep in mind x is being raised to the first power under there. The implied index, if there's none written there, is 2. So if you apply this rule, that says that the square root of x is the same thing as having x raised to the 1 divided by 2 power, or 1/2 power. Once you rewrite, you're able to say then that the derivative, according to the power rule, should be 1/2 times x raised to the 1/2 minus 1, which is negative 1/2. Well, that's the same thing as 1 over 2 times the square root of x. So that's the power rule. The next rule we want to look at is called the constant multiple rule. And it says that if f is a differentiable function and c is a real number, then c times f is also differentiable. And the way you find the derivative, d dx, of c times f of x is that you can take the c out of the derivative and then just take the derivative of the function and multiply it times the constant. So in other words, if you wanted to take the derivative of f of x equals 5 times x cubed, you can leave the 5, the constant, out of the derivative and just take the derivative of x cubed. Well, the derivative of x cubed is 3x squared. Then you would simplify by taking the 5 times the 3 and writing 15x squared. And feel free, once you get comfortable with these rules, to skip this intermediate step and go straight to f prime of x equals 15x squared. You don't need to write that intermediate step. It's just there to help you understand where we're getting our numbers. For f of x equals 5 over x squared, and again, this is a ratio. We're going to need to rewrite it to understand how to apply our power and constant multiple rule. If you rewrite it, you get 5 times x raised to the negative 2. So its derivative will then be 5, constant left out, times the derivative of x to the negative 2, which is negative 2 x to the negative 3, which when you multiply the 5 times the negative 2, you get negative 10 times x to the negative 3, which is the same thing as negative 10 over x cubed is another way to write that. For f of x equals negative x, we talked about the fact that if f of x equals x, then the derivative is 1. Well, that means when you take the derivative of f of x equals negative x, the only difference is there is an implied 1 sitting in front of this x. So you take negative 1 times the derivative of x. Well, the derivative of x is just 1, so that's how we're getting this negative 1. So that's the constant multiple rule. Next, let's take a look at the sum and difference rules. The sum rule says that if f and g are both differentiable, then the derivative of f of x plus g of x is the same thing as the derivative of f of x plus the derivative of g of x. This should look a little bit familiar. We have a limit law that greatly resembles this. Basically, the moral of the story is you can split a derivative across addition. Instead of adding the two functions and then taking the derivative, which is what the left side requires you to do, instead you can take the derivative of the first function, the derivative of the second function, and add them together, which is generally the easier of the two methods. So usually in math, if you have a rule that applies to sums, chances are it also applies to differences. So the difference rule says if f and g are both differentiable, then the derivative of f of x minus g of x is just the derivative of f of x minus the derivative of g of x. So you can split a derivative across subtraction as well. So let's look at an example. Find the derivative of f of y equals 22 times y to the 61st power minus 4 times y to the 10th plus 7y minus 8 times the square root of y. If I had asked you to find this derivative before giving you the differentiation rules, you would have had a limit definition to find. Technically, this wouldn't be x plus h because of the variable. This would be f of y plus h minus f of y. This is not the full definition. There's a limit in front and a denominator, but that means you would have been plugging y plus h into this function. So you would have had 22 times y plus h to the 61st power minus 4 times y plus h to the 10th power plus 7 times y plus h. I mean, this is just a fraction of the limit you were going to have to calculate. And even just look right here. Y plus h to the 61st power is y plus h times itself 61 times. The algebra on this would be horrible. So we're definitely not going to use limit definition to find this derivative. Instead, we're going to use the differentiation formulas we just found. So the derivative of this function, you can either refer to this as df dy, that would be an appropriate way to notate this derivative, or the derivative of f at y, f prime at y. Either one of these is fine, they're interchangeable. Df dx is not okay because your independent variable is y in this case. Okay, so I'm going to use several of the rules on this derivative. So first of all, I notice a lot of addition and subtraction going on. Well, that means I can take the derivative of each term individually. In addition to that, every constant can be pulled out. So I'm going to do this in a couple of steps. I'll take 22 times ddy of y to the 61st power. Okay, remember ddy of y to the 61st means I'm about to take its derivative. I have not done it yet. Minus 4 times ddy of y to the 10th plus 7 times ddy of y minus 8 times ddy of the square root of y. So each one of these, when I take the derivative, will be a power rule application. So that will be 22 times 61y to the 60th minus 4 times 10y to the 9th plus 7 times d dy of y is just 1, and then minus 8 times, remember that square root of y is y to the 1/2. So that's 1/2 times y raised to the 1/2 minus 1, which is negative 1/2. Now I'm going to want to do some simplification here. 22 times 61 is 1,342 y to the 60th minus 40 y to the 9th plus 7 minus, now we have 8 times 1/2, that's going to give me a 4, and then I have a y to the negative 1/2. To get rid of the negative in the exponent, I would move y to the 1/2 to the denominator, but y to the 1/2 is the square root of y. So this is the derivative of this function. And again, as I mentioned, as you get more comfortable with these rules, feel free to go straight to the end product. You do not need to write this intermediate step. It's just me making sure that you know where I'm getting my numbers. Let's take a look at another example. The equation of motion of a particle is s equals 2t cubed minus 5t squared plus 3t plus 4, where s is measured in centimeters and t is in seconds. Find the acceleration as a function of time, and what is the acceleration after 2 seconds. So we start with a particle's equation of motion. This is the equation that gives position as a function of time. What's the relationship between a position function of a particle and that particle's acceleration? If you recall, acceleration is the second derivative of the position function. And remember, there's no way to get to a second derivative without first going through a first derivative. So what we need is the first derivative of the position function, which, by the way, is the velocity function. So again, we're going to split this up across addition and subtraction, and I'm going to skip that intermediate step this time. So the first term, I have 2t cubed. So I take the 3 and multiply it times the 2. That gets me 6. And then I have t raised to the new power of 2 minus 2 times 5 got me 10t. The derivative of 3t, you'll take the 1 times the 3 for 3, and then technically this is times t to the 0, but t to the 0 is just 1. So there's no variable on this one. And then the derivative of 4 is a constant, so its derivative is 0. So this is a function that gives the velocity of this particle as a function of time, which is good, but not what we're looking for. We're looking for the acceleration, so that will be the second derivative of the position function, also known as the first derivative of the velocity function. That'll give us our acceleration. So the derivative of 6t squared is 12t. The derivative of negative 10t is negative 10, and the derivative of 3 is 0. So this is my acceleration function, which will give me the acceleration of this particle as a function of time, measured in centimeters per second squared. So that's find acceleration as a function of time. Now we need to know what is the acceleration after 2 seconds. So to find that, I just need to find a of 2. So that will be 12 times 2 minus 10. That's 24 minus 10 for 14 centimeters per second squared. Let's take a look at another type of common example. We want to find the points on the curve y equals x to the 4th minus 6x squared plus 4, where the tangent line is horizontal. Okay? So we're talking about a curve, so this is a graph that we're discussing, and we want to find out where this graph, where this curve, has horizontal tangent lines. And that's why this is a derivative problem, because when you start talking about tangent lines, you're discussing derivatives. So let's think about this for a second before we go through the actual calculations. This is a fourth degree polynomial with a positive leading coefficient. So what does that mean its graph should generally look like? Well, the end behavior should be up on the left and up on the right. And then this has at most 3 turning points. 1, 2, 3. So this is one of the possibilities of what this graph could look like. But just because a polynomial has the possibility of 3 turning points doesn't mean it actually has three turning points. It could also just have 1, in which case it would look something more along a parabola-ish shape. It is not a parabola, but it's parabola-ish. An example of this one, if you have just y equals x to the fourth, this is more what your graph looks like than having the 3 turning points. So in each of these cases, where do we find horizontal tangent lines? Well, here on this one, on the left side, you would start off with tangent lines having negative slope, and they would stay negative until right about here. And then those tangent lines would switch to positive, and then 0 again. The slopes of the tangent lines would then be negative, then 0, and then the slopes of the tangent lines would go back to positive. So in this particular scenario, there are 3 points where I would have horizontal tangent lines, as opposed to this scenario. How many horizontal tangent lines would you expect to get if this is what your graph looks like? Should be just 1 right here. So we expect either 1 or 3 answers to this question, just to kind of give us a big picture idea of what we're looking for. So we're looking for where the tangent line is horizontal. Well, remember, when you're talking about derivatives, derivatives are the slope of the tangent line. Well, the slope of these tangent lines when they're horizontal is equal to what? Horizontal lines have slopes of 0. So in other words, this is asking you, when do you have derivatives, slopes of tangent lines, equal to 0? So finding where tangent lines are horizontal is equivalent to finding where your derivatives are equal to 0. And if you want to know where something is equal to 0, set it equal to 0. So first, I take the derivative. I'll call this one y prime. You could also just as easily call it dy dx. Either one's great. The derivative of x to the fourth is going to be 4x cubed minus 12x plus, and then the derivative of 4 is going to be 0. So this is the derivative of this function, and I need to set this derivative equal to 0. So we have 4x cubed minus 12x equals 0. It's a polynomial. So we need to factor out what's common to both of these. That's going to be 4x. You're left with x squared minus 3. So by zero product property, either 4x equals 0, in which case x equals 0, or x squared minus 3 equals 0, in which case x squared equals 3, which says that x is plus or minus the square root of 3. So we have a lot of good information here. The question is, does this actually answer the question we've been asked? And the answer is not quite, because the question asks us to find the points. Now what we have are x values. Now how many x values do we have? We have 3. So which of these 2 scenarios did I end up with? Did I end up with 3 horizontal tangent lines or 1 horizontal tangent line? Well, we got the 3. So we know that this has the 3 horizontal tangent lines. This was not the option that we got. So we do, however, need to find the points on this curve. So we need to, let me separate this out a little bit. We have 3 points to find. We need if x equals 0. Now we need to plug in 0 in place of x. So the question is, where do you plug 0 in? Should you plug 0 into the y prime equals 4x cubed minus 12x, or should you plug it into y equals x to the fourth minus 6x squared plus 4? Well, remember what it is you're trying to find at the moment. You're looking for points on the curve, and points are ordered pairs, meaning they have an x-coordinate and a y-coordinate. You do not plug this into the derivative. If you plug 0 into the derivative, what you are finding is the slope of the tangent line at x equals 0. What I'm looking for is the y value at x equals 0. So when we plug in x equals 0, we get y equals, 0 to the 4th minus 6 times 0 plus 4, also known as 4. So we get 0, 4 as one of our ordered pairs. If we plug in the positive square root of 3, then y is equal to the square root of 3 raised to the 4th power minus 6 times the square root of 3 squared, and then plus 4. So the square root of 3 raised to the 4th power, think of that as the square root of 3 squared times itself twice. So that'll be 3 times 3. That's going to give me 9. So that's 9 minus the square root of 3 squared is 3. So that's minus 18 plus 4. So that gives me negative 9 plus 4 for negative 5. So my other ordered pair that I just picked up is the square root of 3, negative 5. And then finally, if x is the opposite of the square root of 3, or negative square root of 3, it shouldn't change my calculations, because if you look, all that's going to do is put negatives in front of the square root of 3's from the previous calculation. But in both cases, you're raising those to even powers, which will cause the negative square root of 3's to have the same result as the positive square root of 3's. So I should get negative 5 for that as well. So my last ordered pair is negative square root of 3, negative 5. Those are the 3 points on this curve where I expect to have a horizontal tangent line. So let's take a look at a couple more differentiation formulas that'll help us in taking some derivatives. The next one is going to be the product rule. The product rule says if f of x and g of x are differentiable, then the derivative of f of x times g of x is found by taking f of x times the derivative of g of x plus the derivative of f of x times g of x. Another way to change that notation to make it a little bit more straightforward is that if you have f of x times g of x prime, the way you find its derivative is by taking f, your first one, times the derivative of the second one, plus the derivative of the first one times the second. Both of these say the same thing, just using some slightly different notation. I wish I could tell you that taking the derivative of the product of two functions was as straightforward as taking their limit. If this were a limit instead of a derivative, you'd just take the limit of the first one times the limit of the second one. But in derivatives, that's absolutely not true. If you want the derivative of the product of two functions, you need the first one times the derivative of the second one, plus the derivative of the first one times the second one. There's a sum in your product rule. Now, that's the bad news. The good news is, in some ways, the order of this doesn't matter. Because of the fact that this contains addition, well, remember, addition is commutative. I could just as easily write this as f prime g plus f g prime. It means the same thing. Also, these are each individually products, and multiplication can go in any order. It's commutative as well. But when you're looking to take the derivative of the product of two functions, what this will boil down to is you will have two terms being added together. In the first term, you need one of the functions times the derivative of the other one. And in the second term, you need to change which original function appears and put in the derivative of the other. Order is a little interchangeable here. Let's take a look at some examples. Use the product rule to find the derivative of h of x equals the product of 3x minus 2x squared times 5 plus 4x. So this specifically asks us to use the product rule to find the derivative, so that's what we're going to do. So this derivative will either be h prime at x or dh dx, depending on which notation you're using. Since we're using the product rule, my first function will be 3x minus 2x squared, and my second function will be 5 plus 4x. So this derivative is given by my first function, 3x minus 2x squared, times the derivative of my second function, 5 plus 4x prime, meaning I haven't taken its derivative yet, I will, plus the derivative of my first function, so 3x minus 2x squared prime, times the second function, 5 plus 4x. So when we actually take those derivatives, what we'll get is 3x minus 2x squared. What's the derivative of 5? It's 0. What's the derivative of 4x? It's 4. Plus, we then need the derivative of 3x minus 2x squared. The derivative of 3x is 3. The derivative of 2x squared is 4x, so minus 4x, times the second function, 5 plus 4x. Now, for the sake of the problem that I have coming next, I'm going to go ahead and distribute and combine like terms for these. So we're going to get 12x minus 8x squared, plus the next one's a FOIL, so that's 15 plus 12x minus 20x minus 16x squared. So that when you combine like terms, you will get negative 24x squared. See, we'll have 24 minus 20, so plus 4x, oops, I forgot my squared, plus 15. And that's the derivative found by using the product rule. Now what we want to do in the next example is take the same function. This is still h of x equals 3x minus 2x squared times 5 plus 4x. We're going to multiply this first. This is a function that can be first simplified by distributing or foiling. So we're going to actually do that first and then use the differentiation formulas that we learned before the product rule to find the derivative and compare the results. So if I simplify first, so this is h of x, this is not yet the derivative. If I FOIL, I get 15x plus 12x squared minus 10x squared minus 8x cubed, which if you want to go ahead and simplify that even further, you can write that as negative x cubed, combine these for plus 2x squared, and then plus 15x. So now we can take the derivative of h by using just the sum and difference rules and the power rule and the constant multiple rules. So the derivative of negative 8x cubed is negative 24x squared. The derivative of 2x squared is 4x, and the derivative of 15x is 15. Compare that to the previous answer. Sure enough, they're the same. In both cases, we get negative 24x squared plus 4x plus 15. So the reason I went ahead and put this example in is because I wanted to make sure I pointed out that while the product rule is not as simple as we would like it to be, it is correct. If you tried to do this the wrong way, generally when students want to do this the wrong way, what they want to do is just take the derivative of the 3x minus 2x squared and multiply that times the derivative of 5 plus 4x. Watch what happens when you do that. Your derivative will then be, the derivative of 3x is 3. The derivative of negative 2x squared is going to be minus 4x. And then your second one, the derivative of 5 will be 0, and the derivative of 4x is 4. So notice when you distribute that, you're going to get 12 minus 16x, which is definitely not what you got there. So just taking the derivative of the first function times the derivative of the second function is usually not going to get you the correct answers. Let's take a look at another example of using the product rule. If h of u equals u times g of u, and g of 3 equals 5, and the derivative of g at 3 equals 2, find the derivative of h at 3. Okay, That looks like a lot of gibberish at first. We're looking for the derivative of h at 3. We're given the function h of u. So can we find the derivative of h? Look at how h is defined. It's u times g of u. That makes it a product. So when we go to find the derivative of h, that will be the derivative of h at a general u. I'll worry about the 3 in a minute. The derivative of h at u, we're going to have to use product rule. We need u times the derivative of g of u. Well, I don't know what g of u is. I didn't define that for you. So the best I have for you is that the derivative of g of u is g prime of u. Plus, what's the derivative of u with respect to u? It's 1 times g of u. So in other words, this is u g prime of u plus g of u. That's the derivative of h with respect to u. So now, if that's the derivative of h with respect to u, what do we get for the derivative of h specifically at 3? That says the same thing it's always said. Plug in 3 everywhere you see u. So instead of u, I write 3. In the derivative of g, instead of writing g prime at u, I write g prime at 3. And then plus g of 3. Now I get to use the given information. G of 3 is 5, and the derivative of g at 3 is 2. So this is 3 times 2 plus 5. This is now just a very simple arithmetic problem. Turns out the derivative of h at 3 is 11. So that's a more general look at how we can apply the product rule. Okay, so here's another example. We're going to differentiate the function f of t equals the square root of t times a plus bt. And again, I've purposely given you one that has a lot of letters on the right-hand side. Your first goal is to identify which of those is a variable. Well, because I've told you it's f of t, that automatically tells you t is the variable in this problem. So what does that make a and b? Those are constants. So we want to take the derivative of this, and we notice that this is a square root of t times a plus bt. So there's a multiplication going on here. And since we've been talking about product rule, let's go ahead and get some practice using that. So I'm going to do this using product rule. So the derivative of f at t, or df dt, is found by the first function. Now keep in mind that the square root of t is the same thing as t to the 1/2. So that's the first function, t to the 1/2, times the derivative of a plus bt. So what's the derivative of a with respect to t? A is considered a constant, so its derivative will be 0. I'll go ahead and write it in. You don't have to, but just so it's obvious where I'm getting my numbers. Then what's the derivative of bt? The derivative of bt with respect to t is b. If you're not sure about that, that one has a tendency to be a little less obvious. Think of it this way. What's the derivative of 5 times t? It'd be 5. What's the derivative of negative 6 times t? It'd be negative 6. So what is the derivative of b times t? It will be b. Okay, so that's how you get that derivative. Plus, I need the derivative of t to the 1/2, so that's 1/2 t to the negative 1/2 times the second function, a plus b t. So if we clean that up just a little bit, that tells me that my derivative, the derivative of f at t, is b times the square root of t plus the t to the negative 1/2 will move down to the denominator along with the 2. So you'll have 2 and then t to the 1/2, but that's the same thing as the square root of t, with a plus bt in the numerator. And that's the derivative. Now that we've discussed multiplication, the product rule, let's talk about the quotient rule, division. So it starts off the same way. If f of x and g of x are differentiable, then if you want to take the derivative of the ratio or the quotient of those two functions, the way you take the derivative of a quotient is you take the denominator as is, g of x, times the derivative of the numerator, so d dx f of x, minus the numerator as is, times the derivative of the denominator, d dx g of x. And then you take all of that and you divide it by g of x squared. That's the denominator squared. Okay, so, or in the slightly simplified notation, if you want f over g prime, that's g f prime minus f g prime all over g squared. Believe it or not, there's another way you can remember this. Most students, if you ask them a year or so after they learn this, what's the quotient rule, most of them will start talking to you about highs and lows. What we do is we say, okay, call f your high function because it's on top, and call g your low function because it's on the bottom. So it's literally their position in the quotient. So then your derivative, your quotient rule becomes low d high minus high d low all over low low. Low d high minus high d low all over low low. Generally, walk into any math tutoring center and ask them for the quotient rule, and the math tutor will probably start talking to you about highs and lows. So that's just another way to remember it. Let's take a look at an example. Find the derivative of f of x equals 5x minus 2 over x cubed plus 4. So this 5x minus 2 is going to be my high function, my numerator, and x cubed plus 4 is going to be my low function, my denominator. So when I find the derivative of this, so f prime of x or df dx, either one, I need the denominator as is, so x cubed plus 4 times the derivative of the numerator. So the derivative of 5x is 5, and the derivative of negative 2 is 0. So that's just 5. Minus the numerator, 5x minus 2, times the derivative of the denominator. So the derivative of x cubed is 3x squared, and the derivative of 4 is 0. All over the denominator squared, x cubed plus 4 squared. Now there is often some kind of simplification that can be done. For this particular example, I'm going to go ahead and skip any simplification just because I want us to be able to concentrate on the actual quotient rule. So notice quotient rule in comparison to product rule is much more stringent about what gets placed where. Let me back up to the previous slide. Because the quotient rule contains subtraction instead of addition, you must go in the correct order in the numerator, or you're going to be off by a sign. You must have, for your first term in the numerator, the denominator times the derivative of the numerator. And for your second term, you must have the numerator times the derivative of the denominator. So order is actually much more important in the quotient rule than it is in the product rule. Now you can still technically switch the multiplication. The multiplication is commutative, but subtraction is not. Let's take a look at a couple more examples where we'd like to maybe decide if we'd like to apply the quotient rule or not. So for example, find the derivative of 1 over x. I definitely see a quotient here, and quotient rule will work. So if I use the quotient rule, I'll have d dx of 1 over x equals, so we'll have the denominator times the derivative of the numerator. Well, what's the derivative of 1? It's a constant, so its derivative is 0. Minus the numerator times the derivative of the denominator. Well, what's the derivative of x? It's 1. All over the denominator squared. So x times 0 is 0. In my numerator, I get a negative 1. And in my denominator, I get an x squared. So that is the derivative of 1 over x. There is, however, a slightly faster way to do this. We have actually already made use of this technique in some of the previous examples. You can rewrite 1 over x using negative exponents. Instead of dealing with it as 1 over x, deal with it as x to what power? That'll be -1. Now you can just apply the power rule instead. Drop the -1 down. You then have x raised to the new power of -1 minus 1, also known as -2. Well, that's the same thing as -1 over x squared. So notice whether you use quotient or whether you first rewrite and use power rule, you get the same result. When you run across a problem where you get a choice, the power rule is probably a little bit faster. Let's take a look at another one. We want to find d dx, the derivative with respect to x, of 5 over the cube root of x squared. Again, when we're taking derivatives that have radicals in them, we need to rewrite using a to the m divided by n equals the nth root of a to the m, which is the same thing as the nth root of a raised to the m. Okay, this is the rule we need to use. So when we go to rewrite this, we get d dx of 5 over, 3 is your index and 2 is the exponent. So this is the same thing as x raised to the what? That should be 2/3. So now we're looking at an example very similar to the one we just did. So you can use quotient rule on this. It's not incorrect to do so, but it's probably just a little bit faster to rewrite this as 5 times x to the -2/3 instead. Notice I'm leaving the d dx here because I have not taken the derivative of this yet. Now that I have it rewritten to where I can apply power rule and the constant multiple rule, I'm going to go ahead and take the derivative. So I will drop the d dx. I will take 5 times the -2/3 for -10/3 times x raised to the new power of -2/3 minus 1, which is -5/3. You can then also put this back into a form much more similar to its original form by taking the -10 and putting the 3 in the denominator. In order to take the -5/3 in the exponent and change it to a positive exponent, you would put it in the denominator and then change from a rational exponent to a radical. So that'd be 3 times the cube root of x to the 5th power. You don't necessarily have to rewrite from here to here, but you're going to see it often in your book, in your solutions manual. When we start plugging numbers into these derivatives, we're going to need to know what it means to raise a number to the -5/3, for example. And all it means is to take the number, put it in the denominator, and then take the cube root of the number and raise it to the 5th power. Let's take a look at another example. Find the equation of the tangent line to the curve y equals the square root of x over 1 plus x squared at the point 1, 1/2. So notice we're right back to find the equation of the tangent line. To find the equation of any line, you only need 2 things. You need point and slope, at which point you can then use the point-slope form. Y minus y sub 1 equals m times x minus x sub 1. We have the point. The point is 1, 1/2. So all we need is the slope. Since this is the tangent line, we need the slope of the tangent line, also known as the derivative. So since we need the derivative of this function, we look, and sure enough, that is going to require a quotient rule. So we take the derivative, either y prime or dy dx, and we use quotient rule. So we get the denominator times the derivative of the numerator. Remember, the square root of x is x to the 1/2 power. So its derivative will be 1/2 times x raised to the 1/2 minus 1 for the -1/2. We then need the numerator, x to the 1/2, times the derivative of the denominator. The derivative of 1 is 0, and the derivative of x squared is 2x all over the denominator squared, 1 plus x squared squared. Okay. So this derivative has quite a bit of simplification that could be done. We could do things like distribute 1/2 x to the negative 1/2 times 1 and then times x squared. That would not be incorrect. We can take x to the 1/2 times 2x. That would not be incorrect. However, we are specifically looking for the slope of a tangent line. We're looking for a number. Assuming I already did all those simplifications, how would I go about finding that number? Well, the derivative is the slope of the tangent line, so you need to plug in an x value, specifically the x value of 1 for this point. So if I'm going to end up just plugging 1 in for x, it's not wrong to do the algebraic simplification, but I'm going to go ahead and just plug 1 in for x immediately, just on the off chance that I might have an algebraic error while I'm trying to simplify. So I'm going to go ahead and just plug in 1. So I get 1 plus 1 squared, which is 1, times 1/2 times 1 raised to the negative 1/2. Well, that's just 1. Minus 1 to the 1/2 is 1 again, times 2 times 1 for 2. Aren't we glad they gave us 1? If they had given us any other number, this would be a lot uglier of a problem. In the denominator, we'll have 1 plus 1 squared, so that's 1 plus 1 squared. So when we're done, we have 2, we have 1/2 and 1 in our first term, minus 1 times 2 gets me 2, over 2 squared, which is 4. This becomes 1 minus 2, which is negative 1/4. So the slope of that tangent line should be negative 1/4. Now that we have the slope, we're pretty much there. We just need the y minus the y value, which is 1/2, equals the slope, which is negative 1/4, times x minus the x value, which is 1. So if we isolate the y, we'll get negative 1/4 x. That will be plus 1/4 plus 1/2 for plus 3/4 total. There is the equation of the tangent line to this curve at the point 1, 1/2. So keep that in mind as we take a look at the next example. This example asks us to find the equation of the normal line to the curve, y equals the square root of x over 1 plus x squared at the point 1, 1/2. So notice I've given you the same curve and the same point. But now we're looking for the equation of the normal line. So the first question you should ask is, what's a normal line? So in general, when you have a curve, and you're talking about this curve at a particular point P, if your tangent line at that point P looks like this, then the normal line at P is the line perpendicular to the tangent line at P. So if this is your tangent line, then this, pretend that goes through P, is your normal line. So these two are perpendicular to one another. They come at a right angle to one another. So if two lines are perpendicular, what's the relationship between their slopes? They're opposite reciprocals. So what we know from the previous example is that the slope of my tangent line was negative 1/4. So what does that tell me the slope of my normal line is going to be? It should be 4. Once you know that, given that you're looking to find the equation of the line, you still only need two things: a point, which we have, and now the slope, which we also have. Believe it or not, once you find the equation of a tangent line, the equation of a normal line is very quick. It's y minus the y value equals the slope, which we decided is 4, times x minus the x value. So the equation of that normal line will be y equals 4x. We'll have minus 4 plus 1/2 for negative 7/2. That's the equation of the normal line to the curve at the point 1/1/2. So I threw this one in here because A, it's going to show up in your homework, and B, you will be discussing normal lines in your physics and engineering classes as well. Let's take a look at another example. At what points on the hyperbola xy equals 12 is the tangent line parallel to the line 3x plus y equals 0? Okay. So we're talking about a hyperbola, xy equals 12, and we're talking about a tangent line to that hyperbola, which means we're probably going to need to involve a derivative. If we need to take the derivative of x times y equals 12, that's not quite the same form we have seen this written in. Normally when we see these, they have already been solved for y or f of x, but the good news is since this is a hyperbola, it's a very easy fix. You just rewrite it as y equals 12 over x, and you'll be able to very easily take the derivative of this. But let's see if we can get a little bit more of a big picture idea of what it is we're looking for. So I have this hyperbola, y equals 12 over x, and remember in general, that is going to be your reciprocal graph, which is 1 over x, stretched vertically by a factor of 12. So it looks something along these lines. This is a different line. This is not a tangent line to your hyperbola. This is some other line. And what you know is that you're looking for tangent lines to this hyperbola that are parallel to this line. Well, it's a line. Let me solve it for y. This is the line y equals negative 3x. So that line has a y-intercept of 0 and a slope of negative 3. So this is going to be a really rough sketch because I don't have any scale on this, but generally this should look something along these lines. Pretend that's a line. Okay. So where on the hyperbola will I find tangent lines that are parallel to this one? Well, maybe right about here, and maybe again right about here. Give or take, those are the lines I'm looking for. I'm looking for the points on the hyperbola that have these tangent lines to them. Okay, so if these two tangent lines are going to be parallel to the red line, what do we know about the slopes of parallel lines? They have to be the same. So I need the slope of my tangent line to be the same as the slope of this red line. Well, what is the slope of this red line? It's negative 3. So listen to what I just said. I need the slope of my tangent line to be the same as the slope of this line. Slope of your tangent line is also known as the derivative, and the slope of this line is negative 3. So the strategy to answering this question is going to be taking your derivative and finding out where is it equal to negative 3. If you want to know where your derivative is equal to negative 3, set it equal to negative 3. So first let's find the derivative. Keep in mind that 12 over x, you could use quotient rule, it would not be wrong, but I'm going to choose to first rewrite as 12 times x to the negative 1. So the derivative, y prime or dy dx, is negative 12 x to the negative 1 minus 1, which is negative 2, also known as negative 12 over x squared. So where is this derivative equal to negative 3? So I take negative 12 over x squared and set it equal to negative 3. A couple different ways to do this. I'm going to cross multiply. So I'll get negative 3x squared equals negative 12, so that x squared equals 4, so that x equals plus and minus 2. Don't forget that plus and minus. That's how I'm going to pick up two different points. So I've solved for x. Does that mean I've answered the question? Not quite. We're looking for points. So these are the x values where I have tangent lines that have slopes of negative 3, meaning they're parallel to this line 3x plus y equals 0. What I now need are the points. So let me go ahead and calculate those. if x equals positive 2. Where should I be plugging in x equals 2 to find my point? You should be plugging into y equals 12 over x. Then y equals 12 over 2, also known as 6. So the ordered pair, so the first ordered pair is 2, 6. And if x equals negative 2, then y equals 12 over negative 2, which is negative 6. So that's negative 2, negative 6, which even according to this rough sketch actually looks pretty good. This would be the 2, 6, and this one would be the negative 2, negative 6. So those are many of our differentiation formulas. We still have one more that we need to cover, but before we do that, we're going to see if we can discover some of the derivatives of trigonometric functions first.